Hello everybody, I'm back again to make another video talking about chemical equilibrium, and this time we're going to focus on how to interconvert the two equilibrium constants that exist that you could express gas phase reactions with. So in the gas phase, let's just take, for the sake of simplicity, a homogeneous, meaning all the same phase, gas phase reaction in my sort of standard form. And we have two ways we can write it. We can have it in terms of molarities. You can always, if you have a volume, you can express the volume in liters. You can always, if you have numbers of things, you can express them in moles if you care to. That's what chemists like to do. And so you can derive molarities for your system, and you can express it as such, with, again, the lowercase letters being the stoichiometric coefficients of the balanced equation, and the capital letters being the species, the particular chemical identities. Similarly, in the gas phase, so you can use Kc like this for solutions or gas phase. Strictly for the gas phase is in terms of partial pressures. So each one of these P stands for partial pressure of the particular species, denoted with the subscript. The subscripts just are telling you which species. The superscripts have mathematical meaning. Those are giving as powers of the pressure. Those are the exponents, and they're going to be the stoichiometric coefficients. In a lot of cases, they're simply ones, but they're still, we want to write it in. For that, the typical input here is atmospheres, although you will see some more select books, physical chem books particularly, maybe some physics papers and so forth, that use a bar, and that's fine. They're very similar values, and if you calculate something in atmospheres, it will have a very similar result to in bars. But you can always interconvert as well. So we're going to focus on what you typically will see in most general chemistry courses on the MCAT and things like that, atmospheres. So let's make a relationship between these two, and I've worked out this. You're not responsible for the derivation, but it is nice to know where this very useful equation comes from. So if you assume ideal gas law behavior, which is convenient because that means there's no interactions going on in terms of potential energy and so forth between the molecules and atoms, it's sort of a hypothetical state, if you will. You can use PV equals nRT. This is the ideal gas law that we talked about last semester. So again, this is the ideal gas law right here. That's an equation over time you probably should know. And so we can set it up where P over RT is equal to, if you divide out, is equal to N over V. Well, think about this. N could be the number of moles, right? And V is volume, and we could choose to make the volume in terms of liters, so moles per liter gives us molarities, right? So for the ith species, I'm just calling the ith species, meaning particular species like P sub C or so have you, the partial pressure of that particular species could have the moles for that particular species divided by the volume of the system, times RT. And so this right here, this term right here, would be the concentration of the ith species. I'm just putting an I in there to mean it's applicable to whatever chemical element, chemical identity you're interested in, for example, C, D, A, or B. And so what we can do then is substitute in for this, let's see, we're going to go to the Kp expression, and now we have these equations in terms of the pressures that we can substitute in concentrations times RT, and we are raising them to a power, which is going to be the stoichiometric coefficient. So all I've done is substituted in for the pressure, concentration times RT, concentration in molarity in each case. What you can do using laws of exponents, from basic algebra, you can separate out the two terms in here, the concentration terms and the RT terms, so you factor out, if you will. And so it looks like this at this point. And this part in front is simply Kc. This is Kc. So that's what I write in the next step here. You have Kc, and then you can, using laws of algebra, write the RT in more succinctly as RT in parentheses. Both of them are raised to the C plus D those are the powers associated with the species in the numerator, which are the products. Those are the products. And A and B are the exponents associated with the reactants. All of these are in the gas phase. So these are exponents that relate to the identity of the balanced stoichiometric coefficients for the species in the gas phase. Now, I wrote something here that was wholly gas phase, but if you had solids or something else in this equation, liquids, you would not write it in. We're not going to worry about problems where, for calculations at least, that are mixed phase of things we're concerned about. Those have particular rule sets usually dictated by journals or books you're using with. So if you have aqueous phase and gas phase in the same system, I'm not going to have you do arduous calculations for KCs with that, where there are different conventions on how to, if you will, normalize that to get a representative K value. We're not going to do that, but we'll deal with here is all gas phase. But if you had something else, some sort of product, let's say E, and it was solid, that wouldn't build in here. That wouldn't build in, so we don't have to worry about it. Meaning these stoichiometric coefficients are just the numbers in front of the product gas phase species and the reactant gas phase species. And so that's the interpretive N. Delta N is, make sure you can see that, delta N is C plus D minus A plus B. So those are the numbers of, again, those are the coefficients in front of the gas phase products minus the coefficients of the gas phase reactants. It's kind of nice because we tend to think of products minus reactants when we're doing calculations. So, and we can write this in a more succinct numerical form. I have to erase the top here because I'm out of space. If you want to have numbers in here, so we have the master equation, if you will, Kp is equal to Kc. And now the R, because we're working in the convention of using R in, we're using, the concentrations of molarity, we're using the partial pressures in atmospheres, we're going to use this R, 0.0820, I'll put it to 4 sig figs, 6 liters atmosphere K mole, or mole K, however you care to write it, times temperature. The temperature is in Kelvin. The temperature's in Kelvin. So we're using the R in the liter atmosphere system. I'm going to put a big asterisk here. That tends to be a confounding point. And this is raised to the delta N, and this is in Kelvin. I'll write K, Kelvin out, because we have so many K's here, they always get confusing. So this is the working form of the equation. Again, regardless of what this is, we're going to report our calculated Kp dimensionless. That means without units. We can take it by convention. There's a deeper theoretical reason going back to the rudiments of the equation, which goes back to a dimensionless entity that's called activity, that we're using concentrations and partial pressures basically as proxies for that, if you will. So we're not going to worry about that. That's getting into more advanced analytical chemistry or more advanced physical chemistry of solutions and so forth. It's beyond the scope of this course. If you go on a chemistry at an upper division or graduate level, they go into that. It's, I even run out of time in physical chemistry to go over it. It's just a point I mentioned a couple times. It is not trivial. It's just we cover a lot of things in a 4-year curriculum. So sometimes some important things do get left out for grad school for those going on further in chemistry. So this is the master equation. Let's do some calculations with it. So this allows us to interconvert between Kc and Kp. Of course, you can always write it in terms of Kc equals. If you want to, you can just divide out the RT delta N. So this, you can always manipulate that equation algebraically, and that's where doing a lot of problems in the skill builders, in the note set itself. I'll put some extra problems up as we move along. And also, if you want even more, you can get a textbook, and really you don't have to use any particular book. Any Gen Chem textbook will have problems on this. You could get a free online copy and just look up equilibrium with gases and interconverting between the think for the gas phase in terms of pressures, in terms of concentrations, they might use a slightly different symbology. It's all good if you know what you're doing. So let's do a couple problems. So I'll start out with a straightforward one, but it's open to its interpretation. That's important. H2 gas plus I2 gas. Let's see here. Goes to 2HI gas, and I just wrote at a certain temperature. K, let's see what I start out with. You can start out either way. Kc is 50. Kc is 50. We know at a certain temperature. So at the same temperature, what's Kp? Well, in that case, the first thing I do when I do this calculation, I have Kc written down here, is delta N. So for this reaction, we have the stoichiometric coefficient here is 2 minus, and then here we have a 1 and a 1. So that's 0. So in that case, Kp is equal to Kc. I'm just going to write it as RT for it to be succinct, and you'll see why. The exponent then is 0. Remember, any number except for 0 raised to the 0 is equal to 1. When you have 0 raised to the 0, we call that an undefined property in math. And so this is Kc times 1. I'm just going to write it as Kc. So in that case, Kp is equal to Kc, and that's equal to 50. You wouldn't believe, sometimes I put this as a multiple choice type question. How many people get this wrong? I don't understand it. So it's this is a way of testing people's conceptual understanding without a hard calculation. So sometimes questions are really simple. So that's one example. In that particular case, Kp was equal to Kc. So let's do something where maybe it's not. So let's take a reaction. So I looked up a known reaction, SO2 Cl2. I'm not sure what that's called. It's gas. And it can reversibly decompose to SO2 gas and Cl2 gas. And I actually wrote down the temperature for this. For example, at 227 degrees Celsius, it's known to have Kc of, let's see, 2.99 times 10 to the minus 7. So a pretty small one. That's, I look at that, I'm not freaked out by something that small. There's plenty of smaller equilibrium constants. It means it's not favoring the products. It's definitely staying on reactant sides, at least at this temperature. Now, we're going to use this equation here. The first thing I always like to calculate is delta N. So delta N in this particular case is, we've got 2. There's a 1 and a 1 here. There's a 1 in front of all these. You don't have to write that. So we got 2, and there's a 1 in front of this. So it's 1. So that means that Kp is equal to Kc. And you have the RT, 80206 liter atmosphere K mole. I really don't have to worry about the units too much. I really have to worry about this number in this particular case, because again, by convention, it's dimensionless, times, and then I'm going to write, this is another key step, you have to convert to Kelvin. So 227 degrees Celsius, I'll just write it as 227 plus 273.15. We'll put it in units of Kelvin. And the delta N is a 1, so I don't have to write anything there. That is not the same as saying it's a 0. It's saying the exponent is just a 1. And here we just plug in the Kc value. I'm not going to rewrite it. I'll just say you squeeze in here 2.99 times 10 to the minus 7. Do out the math on the interior first so you don't make a mistake. And what I got for this is Kp is 1.23 times 10 to the minus 5. So that's what Kp is. Verify it for yourself. And that's a good problem. So, that's a very representative type of problem. It's just a way of interconverting. And of course, if you have something in the form of Kp is equal to Kc, and I'll just write it as RT delta N, you can solve this. You could put it in terms of Kc equals, Kc is equal to Kp divided by RT delta N. So you can do it, both, you can do it in different ways. You can go from Kp to Kc or Kc to Kp readily, depending on what you're doing. And the reason you say, well, why would you want to do this? There's different thermochemical calculations which require different forms of the rate constant, depending on what you're doing exactly. Sometimes you're trying to compare something to a table. The table will be either in Kp or Kc, and you have the opposite, so you need to convert and so forth. So it is a practical skill for real life thermo, so it matters how important you consider thermodynamics in your studies. But this is definitely the type of thing that I put on exams, and if you go on in any area using chemistry, including biochemistry, these type of calculations just are practical. No, it's a good skill. So big mistakes that people make, I would say the two biggest mistakes is, well, I would say delta N tends to be a mistake. People just get that all wrong. The interpretation of delta N equals 0, people tend to get wrong. They tend to treat it as delta N is equal to 1 for some reason. I don't know why. I just see that answer showing up over and over again. And then thirdly, if I do put the problem in Celsius, I usually just look something up. If they give it in Kelvin or Celsius, I say, hey, it's in Celsius. They can convert that. It's converting the Celsius to Kelvin. For some reason, people just forget that step. So these are some of the traps, and I try to let you know ahead of time because I'm not trying to make anybody trip up. I just want you to study hard and get all this. So I'll let you get a good view of the screen. I ensure that I blow it up with my bad eyesight. I can see it on my Android phone. So you should be able to see these. Again, these are not doctored up fancy talks. I want to do just like I do in lecture. So this is the example of how to do Kp and Kc into conversions. Looking ahead in the notes, this corresponds to material starting on page 2. After this, we're going to go into some thermochemistry, the relationships between free energy, delta G mainly, delta G naught, the standard Gibbs free energy, and the relation with the equilibrium constant Q. And then after that, we get into some really important stuff with what we call, used to be called ice tables. I've changed the name to dice tables for social reasons, but it will be a method of figuring out how much, what our composition is at equilibrium for different systems. Very powerful tool. So at any rate, this concludes this lecture. Maybe I'll make another one today. The upload times will take the most time for me. Have a great day, and I'll talk to you later.